Hi, welcome to another video on linear algebra. So we're going to be learning about elementary matrices and the methods for finding the inverse matrix of, for instance, A. So in previous videos we looked up, we worked on how to find the inverse matrix of a 2x2, but how do we find a inverse matrix for some matrix that is like 3x3, 4x4, or any n by n matrix that's greater than 3 or equal to 3. So let's first talk about elementary matrices. Elementary matrices are just obtained by performing row operations from the IN matrix. So what does that mean? Let's look at an example. Let's say we have, let's make the example a different color. Let's say our matrix A is equal to 3, 6, 1, and 2. Okay, and our I, since it's a 2x2 matrix, our I is going to be I2. And our identity matrix is always this. Okay, so if we perform some operation to our matrix A, we want to do R1 times 1/3, and what we're going to do is we're going to try to make our matrix A into a row echelon form. So after I use that operation, I'm going to get 1, 2, 1, 2. Okay, and so this is what the elementary matrix comes in. I applied this R1. I multiplied R1 by 1/3, so that's an operation. So whatever I do to matrix A, I have to do to the identity matrix. Okay. So I'm just going to make a little arrow like this, and I'm going to get my elementary matrix E1, and after I apply that operation, I get 1/3, 0, 0, 1. Okay, so that's my E1, my first elementary matrix. Alright, so we're going to go back to the blue matrix A. We're going to apply one more operation. Let's see if I can fit it in here. We're going to multiply R1 by -1, and we're going to add that to row 2. We're going to get a new row 2. And our new matrix is going to look like 1, 2, 0, 0. Okay, so we have acquired this row echelon form just how we wanted. And so again, whatever operation we perform on the matrix A, we have to apply to the identity matrix. So we're going to apply that row 1 times -1 plus row 2 gives me a new row 2 in our identity matrix. And that's going to be our second elementary matrix. And we're going to get 1, 0, -1, 1. And that is how you find your elementary matrices. Sounds pretty simple. And how do you know if you have the correct elementary matrices? Well, you can check. So in order to check, you have to multiply E1 times E2 multiplied by E1 multiplied by the A matrix. And if you get that equal to the identity matrix, which was 1, 0, 0, 1, you know you did it correctly. A couple things to know about elementary matrices is that all elementary matrices are always invertible with respect to the A matrix. All right. Okay, so a cool example that you might encounter is if you're given the elementary matrix and you're told to find the A matrix that corresponds to the elementary matrix. I think that's a good problem. -6, -6, -6. Okay, so if you can see from this elementary matrix, you acquire an elementary matrix from multiplying or performing a row operation on the identity matrix. And the identity matrix again was just this 1 0 0 1. So how did we get from -6 0 0 1 from this? Well, clearly you can see that you multiplied by -6 to row 1, right? So multiply -6 to row 1. So in order to get the appropriate corresponding A matrix, what you have to do is multiply -6 to row 1, which will give me my new row 1. So we'll get 6, 12, -36, 3, -6, -6, -6. So that's the correct A matrix that that corresponds to this elementary matrix. So that was a good problem to have. Okay, next problems. These are pretty important. It's asking to use the inversion algorithm to find the inverse of the matrix if it exists. That's kind of scary to me, the part of this in the parentheses, because I've never seen where it doesn't exist. Usually the professors are pretty nice and they give us stuff that exists, but I'm actually curious to see an example where it doesn't exist. But what does it mean? It means this. So this is how we're going to set it up. We're going to take our A matrix and we're going to write the identity matrix that corresponds to that A matrix. And then what we're going to do is we're going to try to make that to where we flip positions of the identity matrix, and it's on the left side, and whatever comes out on the right side will be our inverse matrix. Okay, so I'll repeat. We're going to place our A matrix on the left side and our our identity matrix on the right. And we're going to perform row operations to make the left side the identity matrix. And whatever we get on the right side will be our inverse matrix. So let's go ahead and take a look at some problems. Let's try this yellow color. So let's say we're given A is equal to 1 0 1 0 1 1 1 1 0. Okay, so that's our A matrix. And let's go ahead and put it in that way I said. 1 0 1 0 1 1 1 1 0 1 0 0 0 1 0 0 0 1. Okay, so let's take a look at this. On the left side we have our A matrix, and on the right side we have our identity matrix, right? It's a 3 by 3, so that's what the 3 by 3 looks like. You have 1 0 0 0 1 0 0 0 1. Okay. So what we're trying to make it look like, remember, is we want the identity matrix. We want this left side to look like this right side. And whatever is on the right side will be our inverse matrix. So let's start doing some, change the color. Okay. First thing we're going to do is you're going to multiply our 1 by -1, and you're going to add it to row 3, and that's going to equal row 3. And remember, you always want to start with one column. Okay, so you want to make this a 1, this a 0, and below that a 0. So work on column by column, and you'll get the left side to look like the identity matrix in no time. So if we go ahead and perform those operations, we're going to get this 0 1 1 0 1 -1. It's going to be 1 0 0. That's a 0 0 1 0 -1 0 1. Okay, and we're going to do another operation. That's going to be R2. We're going to multiply that by -1 and then add it to R3, and we're going to get a new R3. Okay, I'm going to put that below this one. That's going to be 1 0 1 0 1 1 0 0 -2. Okay, that's going to be 1 0 0 0 1 0 -1 -1 1. Okay, so as you can see on the left side, we have this column done, this column's done. Now we just have to work on this column, this third one, and we want 0 0 1. Okay, so it's gonna be a couple operations. Well, what we could do is we can do row 3, and we can multiply that by -1/2. That'll get you a new R3. And that'll be 1 0 1 0 1 1 0 0 1. It's gonna look like 1 0 0 0 1 0 1/2 1/2 and -1/2. Okay, we're gonna do 2 more operations. We could do R3 -1 plus R1, and we could do R3 -1 plus R2. Okay, so you're allowed to do 2 operations at the same time as long as they're being operated on different rows. So here we're changing R3, but what we're doing is really operating on R1 and R2. So 2 different rows, totally legal move to make. You're in the clear. So what we'll get from that is 1 0 0 0 1 0 0 0 1. And on the right side, we have 1/2, -1/2, +1/2. -1/2, you have a 1/2 there, 1/2, and you have a 1/2, another 1/2, and a -1/2. Okay, now let's take a look at our final product. On the left side, we have what looks like our identity matrix. So, by the algorithm, that means that on the right side we have our inverse matrix. So, our inverse matrix, A inverse, is equal to 1/2, -1/2, 1/2. Yeah, it's that. Negative 1/2. 1/2. I'm going to scribble because I don't have room. But you can see that in the gold or yellow. So yes, that is our inverse matrix. Whatever you have on the right side, that's your inverse. And that's how you perform the algorithm. So that'll conclude the video on how to find the inverse matrix and finding your elementary row matrices. So hopefully that was helpful. And in the next video, we'll definitely be using this algorithm technique a lot. So thanks.